morning, everyone. Welcome to our talk. Today, we're going to talk about how to improve data source V2 query planning using column statistics. A quick self-intro first. My name is Huaxin Gao. I'm a software engineer at Apple. I'm also an Apache Spark PMC member.
Hey, and I'm Parth Chandra. I am Apache Drill PMC. I'm an initial contributor to Apache Arrow, and I'm also a software engineer at Apple.
Here is the agenda of today's talk. First, we will talk about the motivation of our work. And then we will give a brief overview of the Spark query optimization. After that, we're going to talk about the data source V2 statistics collection framework. And in the end, we're going to talk about the TPC-DS benchmark result and some of the query analysis. The motivation of our work is to experiment cost-based optimization in data source V2. When we did the TPC-DS benchmark using Apache Iceberg, we have observed some of the queries are really slow. So in order to solve the problem and make these queries run faster, we have decided to take advantage of the cost-based optimization in Spark. Originally, the cost-based optimization only works for data source V1. So for us, in order to experiment cost-based optimization in data source V2, we have introduced a couple of the new interfaces, and we make the V2 data source implement the new interface. So we can collect the column statistics from V2 data source, and then report this to Spark. And Spark can use this statistics to calculate the cost of the physical plan, and then it will pick the most optimal plan to use. I will handle things over to Parth, who will give a brief overview of Spark query optimization.
Thanks, Huaxin. So this is probably a well-recognized picture. Let's go over it very, very quickly. This is an overview of how Spark does query planning. We start with a SQL query or a data frame, and Spark will produce an unresolved logical plan from the input. The unresolved logical plan at this point has not resolved column names or field names or table names. In order to do that, Spark will look up a catalog, and from the catalog, it will determine types and names of the columns and the tables that it needs to read. Given all this, it produces a logical plan. This is simply a plan of how the query can be executed to produce the results that are required. On top of the logical plan, you apply a bunch of logical planning rules. Now, these rules improve the query plan, but transform the query plan only so that it will also produce the same results as the original plan would. Right? So this is every step of optimization always produces a new plan which has to produce the same results. The next step is physical planning. At this point, you start resolving what are the actual operators you're going to use, how much parallelism you need, and you take all kinds of factors into account here. And the result of this is a bunch of physical plans, all of which can produce the same output. But naturally, some plans are better than others. And that is the point at which cost-based optimization comes in. You apply a cost model which tries to evaluate the cost of every single one of these physical plans. Actually, when I say every single one of these, we don't actually evaluate all the plans. But we do try to go from a plan to a better plan, and then find the next better plan, and so on, until we come up with a plan that is way better than what we started out with. So the cost model requires a whole bunch of input that isn't part of the original source, but which can be derived from the original source of data. Once we've got that, we have a physical plan, which is then, you do some code generation, and you execute the plan. So in Spark's query optimization, the first step, as we mentioned, we go from, we're applying some rules to the logical plan. We apply rule-based optimization. This is standard query optimization. And the basic principle we apply at every step of query optimization, and this in fact works for any large-scale data processing, or in fact any data processing at all, is that you want to reduce the amount of data as much as possible, as early as possible. This is the invariant that every single one of these rules is designed to implement. So two very common examples that are applied by every engine are filter pushdown and column pruning. Now, filter pushdown applies a filter or a predicate condition to the source data. And this is as soon as you can apply it. It can be sometimes part of the scan itself. And naturally, as you can see, this will reduce the amount of data that you even read, let alone process. The same thing with column pruning. Don't want to read any columns if you don't need to actually process them at all. So again, you're reducing the amount of data that has to be processed. Cost-based optimization is a little more complicated. It uses properties of the data itself, values, row counts, the number of rows in the table, the size of a row, the size of each of the columns, min and max values, and so on. And as we said, that this is to decide which of the physical plans that we are going to use has the lowest cost of execution. So with cost-based optimization, one of the most useful and important things that we do is to decide on joins. Now, when I said we resolve a physical plan, we create a physical plan, we're trying to, let's say we use, the logical plan has a join in there. But the physical plan will tell you which particular type of join you want to execute. Can you use a hash join here? Can you use a broadcast hash join, or should you use a shuffle hash join? If you cannot use a hash join, should you fall back to a sort merge join? Now, each of these has a different cost of execution, and you would prefer to use a broadcast hash join over a shuffle hash join over a sort merge join. But in order to know which one of these you can use or should use, you need to apply the costs or apply some statistical information to estimate how much data is going to be produced by each choice of join. And in queries which have multiple joins, you have not just a choice of join operator, you also have a choice of which order to execute the joins. You have join between tables A, B, and C. Should you do A and B first and then C, or should you do B and C first and then A, and so on? And as the number of these tables that you're going to do joins on increases, the number of these combinations increases, and you have to do more and more computation in order to find which is the best possible order. So today in Spark, the cost-based optimization requires you to run an analyze table command. The analyze table command is the command at which you collect the information that the cost-based optimizer is going to need. And this is the information that is derived from the source data. At the table level, typically, you always want to know the number of rows and the size of the rows. Basically, you need to know the total size of the data in bytes. Similarly, and particularly for join and predicate estimations, you want to know properties of every single column. So the analyze table computes statistics for column command will do that for every single column. And as you can see, if you have a large amount of data and you have very large tables with many, many records, just computing this information can take a lot of time. For numeric data and timestamp types, we collect a whole bunch of values: distinct count, max count, main, null counts, and so on. And for string and binary types, we collect distinct count, null count, and so on. And of these, distinct count is one of the most useful bits of information that we can derive. As you can see, it's also one of those pieces of information that require you to do a bunch of computation. It is, in fact, an aggregate. It's the same as select distinct count. And if you have terabytes, petabytes of data, this can take a while. And now, remember, we're not just doing it for one column, we're doing it for pretty much every column that we want to process in our queries. So as Washington mentioned, this information doesn't exist for V2 sources. And to tell you how we figured that one out, it's Washington.
Thank you. So as Parse has just mentioned, if we want to use cost-based optimization in data source V2, the first thing we need to do is that to trigger the statistics collection. But unfortunately, currently the analyze table command doesn't work for V2 data source yet. And also currently, we don't have a way to report the column statistics back to Spark. So if we want to use cost-based optimization in V2 data source, we need to lift these two limitations first. I will show you the data source V2 API framework and how we improve the data source V2 API to support cost-based optimization. This slide shows the data source V2 API framework. The data source V2 API was introduced in Spark 2.3. It has a bunch of Java interfaces. These Java interfaces are located in Spark SQL connector packages. I listed some of the basic API here. For example, it has a supports pushdown filter API, and it also has a pushdown required column API. Remember the golden rule of optimization Parse was talking about earlier. So in any kind of database optimization, we want to reduce the data as much as possible and also as early as possible. That's why the DSV2 has the supposed pushdown filter API and also the supposed pushdown required column API. But today, the API we will focus on is this supposed report statistics API. Because if we want to use cost-based optimization in V2 data source, we will need to report the statistics on the V2 side to Spark. Currently, there isn't a way to report the column statistics. So that's why we add a new column statistics interface in the V2 API. So basically, in this API, we collected the distinct count. We collected the mean, max, and also the null count. We also collected the average length, the max length, and also the histogram. So for V2 data source, if it want to use cost-based optimization, it will need to implement this interface. I will use Apache Iceberg as an example to show you how we implement this column statistics interface and how we collect column statistics from the V2 data source. So just in case you are not familiar with Apache Iceberg, I will talk a bit about this Apache Iceberg. So basically, Apache Iceberg is a high-performance format for huge analytic table. It supports transactional consistency, time travel, schema evolution, partition evolution, and quite a few other advanced features. For engine support, Iceberg supports Spark, Trino, and Flink. For Spark supports, Iceberg implement data source v2 API. So for Iceberg, if we want to use cost-based optimization, we will need to trigger the statistics collection on Iceberg first. Since the analyze table command is not supported by Iceberg, it's not supported by V2 data source yet. So for us to do the experiment, we have implement a stop procedure on Iceberg side. This stop procedure is pretty much the same as the analyze table command. So for this stop procedure, you can specify the name of the table, and you can also specify the column of the names you are interested in. So when you call this stop procedure, it will trigger the column statistics collection on the Iceberg tables. So for Iceberg table, we have collected the mean, max, and null count. Actually, in the stop procedure, we have called this select mean, max, count from table. But actually, to collect this mean, max, and count, we don't need to do a table scan. Because in Spark, in V2 data source, there is a feature called aggregate pushdown. We can push down the aggregate function to the data source layer. So we push down the mean, max, and the count to the Iceberg side, and we get the information from there. On Iceberg, there is a manifest file. Basically, it is the metadata file, and it contains a bunch of statistics, including the column mean, max, and count, the number of nodes. So we get all the aggregate function, I mean the information, the mean, max, and null from the manifest file. It is much more efficient than getting this using table scan. In order to use cost-based optimization, another important statistics we want to collect is the number of distinct count. Because this number of distinct value is very important for compute the cardinality of join. So it is actually quite challenging to get the number of distinct values for big data. The main reason is that the number of distinct value is not additive. So for example, if you have the number of distinct value for group A, and you also have the number of distinct value for group B, if you want to get the number of distinct value for these two groups combined, you cannot simply add these two numbers of distinct values together. Because very likely there's some common values in between of these two groups. If you simply add the two numbers together, you overcount this number. So since the number of distinct value is not additive, the parallelization doesn't help much. And also, there isn't a good way to compute the incremental update. So it's really expensive to get the number of distinct value for big data. And then how should we do this? How can we collect the number of distinct value in a more efficient way? The answer is that we can use DataSketch. What is a DataSketch? So simply speaking, DataSketch is a way to make the big data small. It models the problem as a stochastic process and then analyzes the problem using probability and statistics. Let me give you a very simple example. So imagine you go to a fair and you want to play the guess how many candy in the candy jar game. And there is a huge jar of a huge candy jar, and in the jar it filled with the chocolate. So you want to guess how many, what's the number of chocolate in this candy jar? You cannot count one by one. So I guess the approach you may want to use that you try to somehow count a small portion of the chocolate, and then use this number you scale up and estimate the number of chocolate in the whole candy jar. So DataSketch using the similar approach to solve the problem. But of course, DataSketch is much more complicated than my count candy example. But similarly, DataSketch will also pick a small amount of the data. It picks this small amount of data in a very smart way. And then it kind of threw away the majority amount of data. So for this small representation of the data, DataSketch will do some analysis to get the result. And then it will scale up to get the approximate result for the whole data set. I listed some of the important properties for DataSketch. First, the DataSketch is really small. It is usually orders of magnitude smaller than the real dataset. Also, DataSketch is sublinear. Sublinear means that it grows very slowly, and also it has a finite upper bound. So in another word, the sublinear means that the DataSketch is very small, and it can remain to be very small regardless of how fast the real data grows and how big the real data grows. Since the DataSketch is really small in size, it is really fast to analyze the data. So it is usually orders of magnitude faster than analyze the real data set. Another very important feature for DataSketch is that it is additive. So it is mergeable. You can merge the two data sketches together. So it is really fast to calculate the incremental update. The result for DataSketch is approximate, but there is a mathematically proven error bound. I will talk a bit about Apache DataSketches. Apache DataSketches is an open source implementation of DataSketch. So it is a software library of stochastic streaming algorithm. Apache DataSketches has 4 important families. So it has a distinct count family, It has a quantiles and histogram family. It has a frequent item family, and it also has a sampling family. For us, since we need to collect the number of distinct value, so we are interested in the distinct count family. In this distinct count family, it has implementation of the famous hyper-log sketch. The implementation is really fast. And also, it has the implementation of Theta Sketch. For Theta Sketch, it supports more set of operations, such as union, intersection, and difference. It also has CPC sketches and tuple sketches implementation. In Spark, to calculate the approximate count distinct, Spark has its implementation of hyperlog ++. Very recently, I think in March, Spark has added the support for Apache DataSketches. It uses Apache DataSketches hyperlog sketch to compute the approximate count distinct. More importantly, Spark has added the ability to store the intermediate storage for hyperlog sketches. So after this, we can calculate the incremental update for NDB in a much more efficient way. In Iceberg, in order for us to compute the number of distinct value, we have decided to use Apache Sketches Theta Sketch. The reason we want to use Theta Sketch instead of hyperlog sketch is that in Theta Sketch, it has more set operation. It supports union, intersection, and difference. But for hyperlog sketch, it only supports union. Another important reason we want to use Theta Sketch over hyperlog sketch is that some other engines, such as Trino, uses Theta Sketch. So for engine interoperability, Iceberg chose to use Theta Sketch instead. After we compute the Theta Sketch, we want to persist this information to the table. In Iceberg, there is a table-level Python file. So it is a table format for sketch. We can just store the Theta Sketch in the Python file. If we want to compute the incremental update for number of distinct value, we can just simply re-aggregate these sketches. It is really efficient to get the incremental update. Now we have collected all the information, all the statistics we want. And the next step, we need to report this statistics back to Spark, and Spark can use this. So in order to report the column statistics back to Spark, we made Iceberg to implement this column statistics API, and then this information will be reported back to Spark. On Spark side, when Spark sees this V2 data source V2 statistics, it will convert the DSV2 statistics into a regular statistics. And then Spark will use all these statistics to compute the cost of the physical plan. And then it will pick the most optimal plan to use. So I hope with my explanation, now you have an overall picture of how cost-based optimization works for V2 data source. With this, I will turn the control to Parse, who will talk about the TPC-DS benchmark result and some of the query analysis.
Thank you again. Thank you again, Fashin. So we did a TPC-DS benchmark, and let's talk a little bit about those results. So the benchmark was run on a scale factor of 1,000. That's a 1 terabyte data set. We ran it on an AWS EKS cluster, which was running Debian Linux. We had 32 executors, each with 8 cores and 64 gigs of memory, and the driver had 32 cores and 512 gigs. Our base Apache Spark version was 3.3, and our base Apache Iceberg version was 1.2.0. So here's a very quick overview. I know it's a little crowded because there's a lot of queries in TPC-DS. Let's see, yeah, it should be somewhat visible. The blue line is the baseline, and the green line is after we turned on data source V2, stats, and the cost-based optimizer, and join reordering. Just a very quick summary, we got a 15% improvement over without stats and without CBO. It's a little smaller performance improvement than we had hoped or expected to get. But query 72, which is that long blue line, which was the worst performing query in the entire TPC-DS benchmark for us, had a 4-time improvement. It was 4x faster. So let's spend a little bit of time talking about that. So query 72 has 9 tables. It has 4 fact tables and 5 dimension tables. It does 11 scans. One of the dimension tables is scanned, it's the date dimension, is scanned 3 times. It has 8 inner joins and 2 outer joins. So if you are going to do join planning and improvements in join planning, this is a fun query to work with. This is what the query looks like. Now, I know it's a little long query, it may not be very easy to read, but I'd just like to draw your attention to the beginning. Let's see if we can point to that. Oh, sorry. Oh, never mind. So the initial join conditions, look at the very first join condition. The very first join condition is on catalog sales and the inventory table. And these are 2 very large fact tables. So this query is written in a way in which all the joins involving fact tables are written first, and then the dimensions are actually listed in the end. This is what the plan looks like. And without any optimization or without any of the cost-based optimization in play, this plan actually looks exactly like the query was written. Here's how it looks visually. It's a little bit easier to read. And like I said, the catalog table and the inventory table, the catalog sales table and in the inventory table are joined first. And the other thing that strikes you immediately, this is a query plan that's leaning very heavily to one side. What that means is that you have to do the first join while everyone else waits. Then you have to do the second join, and so on and so forth. It's very, very linear. There's not much scope for doing things in parallel here. The other thing that should maybe strike out immediately is that the very first join is a sort merge join. Remember, we said that sort merge join is our last choice when you want to choose the type of join, because it is the slowest. It involves a shuffle, and it involves a sort, none of which are fast. And not only that, but if you look even more closely, we started with a few 100 million records in one table and 750 million records in the other table, and we ended up with 47 billion records. So we did not, in fact, follow our basic rule of trying to reduce the data. It actually exploded the amount of data that we have to work with. There's a very important reason why this query was taking so long. And this is just the beginning, because if you look, subsequent joins are also sort merge joins, and they are not doing a very good job of reducing the amount of data that we have to process. So the query spends all its time sorting, merging. Now, when we turned on cost-based optimization, it's maybe not so obvious from this query plan here, so let's look at the picture. The plan changes drastically. For one, it's not leaning heavily to one side. And if you look even more closely, you will see that the very first join involves catalog sales, which is a fact table, and household demographics, which is a dimension table. And if you look even more closely at the numbers, the dimension table has a very small number of records. So clearly, we can use a broadcast hash join right here. And if you look at the result of this particular join, the number of records that you get is much, much smaller than the number of records that you started out with. And that's exactly what we wanted to do. The other thing that we had, which was, well, here was a plan which was completely linear. Every join had to follow the other. It's no longer the case here. We have, it's called a bushy plan or bushy tree here. And the inventory table, which was the other very large table in this particular query, is on the right-hand side of this plan. And it's a little more complicated. And in this particular case, you will see that actually at one place, one join actually increases the amount of data, but then it manages to reduce the amount of data very rapidly after that. And you don't hit a sort merge join until the very end, in the last couple of joins, and those happen to be the outer joins, so it was kind of unavoidable at that point because you've reduced the left-hand side of the query plan and the right-hand side of the query plan as much as you possibly could, and you still had a very large number of records. So this is how, by just better planning, this particular query managed to be 4 times faster, still process the same amount of data to start with, but the total amount of data that it had to process was much, much less. So we did have to make a couple of fixes, and changes, and improvements in the Spark side of the query planner and the estimator. We had to make changes to the union statistics. We had to make some changes to the string type statistics, and these are being tracked in the open source implementations. So anyway, that's what we have for you guys today. Thank you. We're ready for any questions if you have any. We have